Recording in progress.
No idea. I think she said she was.
Hey Ross, is everything still intact at your house?
Yes.
Yep. Annika has a doctor's appointment today. But yeah, we're getting down towards the end here.
Home straight.
Home straight. That's right. Yeah, her maternity leave starts tomorrow, actually. So it's like tomorrow's her last day of work for 6 months, so that should be good. I think she's pretty ready to not be working right now.
Yeah.
Focus on growing a kid, you know, those important things.
Yeah. Should we wait for a few more people to turn up?
Sure.
Yeah, we're waiting on a few here, so.
Okay. Claire, did you manage to kick out those important people?
Yeah. You're very nice about it.
Oh, good.
You still have time. You still have time. Talking, and hopefully anybody has to skip a day, then they can let other people know.
Yeah.
Slide in.
Or if there's any emergencies, we gotta do something.
Yeah.
Are you friends with Claudia on Facebook?
Yes.
Okay.
Yeah. Make sure she's ready. Already or not?
No, I'll check
Just,
that.
I don't mind to add you to maybe mark it. Yeah. What about your email? Okay.
Maybe just give it a go and people filter in when they filter in.
Okay. Sounds good to me. Oh, hi, everybody. Today we have a very special guest speaker. Clare Wilkinson is someone that I've been working with for the last 4 years, I guess. Is that right, Claire? 4?
About, yeah.
Yeah, I'm very proud of her. So I'll do my wee spiel. So our speaker today is Dr. Clare Wilkinson. She came to us a few years ago from the US as a fresh-faced, quietly determined PhD student. She encountered a few hardships and holdups due to new cosmogenic premises and difficult samples, which she overcame stoically with a little help. She blossomed before our eyes. She blossomed before our eyes over the years from that quiet presence into a respected scientist. This culminated in her being the keynote speaker at the 2020 GSNZ conference and an appearance on both TVNZ Breakfast and Māori TV's Te Ao Tapatahi, plus publications in Geosphere and Earth Surface Dynamics. Claire completed her Bachelor of Science with honours in geology at Washington and Lee University in Virginia, USA, where she studied bedrock river erosion. She recently completed her PhD in the School of Earth and Environment at the University of Canterbury, where she studied landscape change after major disturbances. Her doctoral work wove together fluvial geomorphology and indigenous Māori knowledge to better understand how the Conway River responded to the 2016 Kaikōura earthquake. She employed a series of different methods, but today she'll be focusing on the cosmogenics work that she conducted in collaboration with Tim Stahl, Kevin Norton, David Fink, and Toshi Fujioka. This work is currently in review with Earth and Planetary Science letters. Claire is currently working as a research assistant for the School of Earth and Environment and is starting a new role as a fluvial geomorphologist with Tonkin and Taylor in November this year. It is my pleasure to introduce her to you. Thanks, Claire.
Oh, thank you, Stasha. I think you could be a news reporter. Well, that was very kind and very generous. Thank you. I'll just get my screen share going. Can everyone hear me all right? Yeah, okay. Perfect. Cool. Cool. All right. So thanks again, Sasha. So today I'm going to be talking about, as Sasha said, a subset of my PhD research, and that is the cosmogenic side of things. We have a paper currently in review under the same name, and so pretty much what I'll be sharing with you today is everything that we've got in review in that paper. And so the title of this work is Delayed or Absent Beryllium-10 Dilution in Detrital Quartz Following Extensive Coseismic Landsliding, the 2016 Kaikōura Earthquake Case Study. And so I'd just like to take a moment to acknowledge my co-authors, who Sasha's already mentioned, but would also like to additionally acknowledge Katie Jones, who didn't specifically help with the cosmogenic side of things, but is a co-author on the paper because she was very generous and contributed some important information about the landslides in this river catchment. And so just for some background, this field area is on the South Island of New Zealand in the Kaikōura area. In 2016, there was a magnitude 7.8 earthquake, and it was one of the most complex earthquakes ever recorded. And so this map here in the middle of the screen is one of the areas a bit north of the town of Kaikōura that was very heavily impacted by fault rupture. And so in this area, there was up to 8 meters of vertical offset and between 4 to 6 meters of horizontal offset on some of these faults. And that those numbers specifically come from the Papatea fault, which is here. So those were some of the biggest kind of fault offsets that were recorded in this event. And on the right here are some pictures from Rob Langridge and others from a publication that they put out in 2018, showing some of those fault ruptures and these really big changes to the landscape. One of those really big changes was the amount of landsliding that occurred during the event. And so almost or around 30,000 landslides were triggered in the Kaikōura event over the affected area, which you can see in this map from Chris Massey and others. And some of these landslides were very highly concentrated in certain areas, and that's an important point that we'll come back to a bit later. And so this landslide material has varying degrees to which it is connected to the river channels below. But in some cases, so much of that landslide sediment has entered rivers that in places there have been up to 25 or so meters of aggradation downstream of some of these really, really large landslides. And so it's a pretty incredible landscape to have been able to work in, very dynamic, amazing rivers, and really neat place to study how the landslide sediment is moving through these catchments. And so the methods that I used were employed in the Conway River were developed by West and others in 2014. And essentially, they're using beryllium-10 in detrital quartz as a tracer of this coseismic landslide material. So I know all of you will be very familiar with beryllium-10 attenuation with depth, but just really briefly, what this plot is showing is that for a sample that is at a low depth, so essentially at the surface, it will have a very high beryllium concentration relative to samples that were at depth. So we have increasing depth here on the y-axis, and so a deep sample having a very low beryllium-10 signal. So the idea is that if we have an earthquake that triggers a whole bunch of deep-seated landslides, this low beryllium material from the landslide failure area will mix in with the stream sediment and dilute the overall beryllium concentration of that river sand. So here's another plot from the same publication that kind of shows their theoretical approach with some real world data points explaining that idea. So here again, we've kind of got our high beryllium concentration samples, and then whoop, there's a big earthquake. And now those samples, or the samples from the same locations, are showing a much more dilute signal of beryllium-10 as a result of that deep material that has been liberated from the hill slopes. And so kind of the idea is we can use this beryllium-10 to trace the coseismic landslide material as it mixes with the river system and moves downstream through time. And just wanted to show a quick picture of the landscapes for which this method was developed and where I have applied the method. And so on the left there is a picture of one of the landscapes affected by the 2008 Wenchuan earthquake, and on the right is my study area for the 2016 Kaikōura earthquake. So lots of landslides in both landscapes, different types of landscapes, but putting the method to the test in both of them. So a bit of information about the Conway River. The Conway is located a little bit south of the town of Kaikōura. So this is the Kaikōura Peninsula here, and the town of Kaikōura is just around there. Hopefully everyone can see my mouse. And the Conway River and the catchment area experienced over 2,500 landslides during the earthquake event. Within the catchment, there was a total affected landsliding area of 3.66 square kilometers. And for the whole catchment, that landsliding area equates to 0.75% of the total area having been affected by that landslide area. And using landslide area to volume relationships that have been developed specifically for these landslides by a team at GNS Science, we estimate that there's around 12.3 million cubic meters of landslide material that was generated in this catchment during this event. And so we were interested to see if we could trace this landslide material as it was moving downstream. We had 3 sampling campaigns, the first of which was in late December and early January. I think it kind of was right around the Christmas New Year holidays. And it was also about a year after the Kaikōura earthquake. So that was our first sampling campaign. Then we had a second one in February of 2018 after ex-tropical cyclone Gita, which delivered quite a bit of rainfall to the region. And then we had another sampling session in July of 2018, again following some very heavy rainfall. And so the idea of picking up those samples after the rainfalls was because we were thinking, oh, there'll be more sediment mobility in those times, and so it will be hopefully beneficial for us in terms of that sampling campaign. So we targeted less than 500 micrometer sands for fresh deposits, from fresh deposits for our analysis. and also collected some larger sediments from the same sample locations as well. Now this is a map. It's a busy map, but we'll walk through it to show where these sample sites are located. And I'll first draw your attention to the Conway River, which is this gray catchment on the right and the little inset. So within the Conway River, we had 4 sample sites, 3 of which were located at the rangefront. And so if we look at this kind of expanded map of the headwaters, you can see 3 little dots, and the black and the orange dots represent these 2 main headwater tributaries from which we collected samples, and this blue dot represents a sample location below the confluence of those 2 tributaries. So we were able to try and tease out the relative contributions of those 2 tributaries. And then the final sampling site for the Conway River was much farther downstream. It's this green dot here, near the outlet of the catchment. One thing that kind of complicated this work was that we don't have any pre-earthquake beryllium 10 concentrations for this river catchment. And so what we did to kind of make up for that was we also took a sample at the same sampling intervals from the Hurunui River, which is this big blue catchment. And though they're very different in spatial scales, the important thing about the Hurunui River is that it was the closest catchment to the Conway that was unaffected by landsliding and fault rupture during the Kaikōura earthquake. And so essentially what we were doing was we were monitoring a nearby catchment to see if there were any fluctuations in the beryllium 10 in the absence of these coseismic landslides. And so after collecting my samples, I had the privilege to go up to Victoria University of Wellington and work with Kevin and Clare Wilkinson there to work on my tough samples. These samples come from the majority of gray wacky lithology. So there's quartz in there, but relative to the other stuff, there's not that much quartz. And so it was a bit of a trouble trying to get this clean quartz out of these samples. But Kevin and Claire were awesome and helped me get these samples in good shape, and at which point we could send them over to David and Toshi in Australia, who passed them through the AMS for our team. And so here are our results, and I'll walk you through each of these ones as well. Some quick things to note before diving in too deeply is that the solid boxes represent the less than 250 micron grain size, and the hashed boxes, if there are any next to those solid boxes, represent the corresponding 250 to 500 micron grain size from that same sample location. 2 samples were unfortunately lost in an oven accident. We had a bit of an explosion and unfortunately couldn't recover those samples. But those 2 samples, you'll see these gaps here in the timeline for these 2 tributary samples. That's what these 2 on the top here are from. And then another thing to note is that we had 2 samples that had quite high boron contamination, and that was this one, the Tūtae Robson, July 2018, and the Conway State Highway 1, which was one of the downstream outlet samples, also from July 2018. So I just wanted to mention all of that before we kind of look at the results. But so what we were looking for was some sort of dilution or some sort of change to see if we could detect how this river was responding to the landslides by using beryllium 10. And what you will probably have noticed by now is that there really weren't any discernible changes in any of our samples. In the headwater samples, the 2 main tributaries, they were extremely close to being the same values. And even when it looked like there could have been some change, they were still in the one standard error of each other. And same thing with the sample from below those two tributary confluences, and not much change and falling within or very close to their one standard error. And same thing at the Conway River outlet. Sorry if my mouse is moving around. I've lost it on my screen, but wanted to show you. Anyway, so the Conway State Highway 1 samples were the catchment outlet. And again, everything's kind of falling in that one sigma error. And then the Hurunui samples, those were meant to be our reference samples, were showing that, yeah, there weren't very many, if any at all, natural fluctuations taking place in that catchment in the absence of those coseismic landslides. So really no discernible change within the roughly 1.5 to 2 years following the Kaikōura earthquake. So the next thing we did with those results was we used them to determine the catchment-wide apparent erosion rates. And so that's what this plot here is. The blue line at the top, and then again in the main graph, represents the hydrograph for the study period. And so it's important to note that there were some high flow events before our first sampling period. So that would be in between the earthquake and before the first sampling period. But we were able to capture the largest rainfall event since the earthquake with our third sampling campaign. And so despite those precipitation events, we didn't see the change that we were expecting to see. And when we were looking at these values and these data in terms of the catchment-wide apparent erosion rates that they represent, we determined or realized that the samples that were close to the range front, so the samples that are outlined in red there, they're very close to the same rates that some other researchers had determined for the exhumation rate of the range front. And so these samples were essentially indicating that the erosion is on pace with the exhumation rate in the range front. And so not really showing that diluted beryllium signal and not really showing any change in the erosion rates. So that kind of posed some other questions that that required us to do some additional analyses. And this is kind of where we brought Katie Jones on board to help elucidate what some of those landslides were doing. So we looked at the immediately post-seismic landslide channel connectivity values, which is essentially how much and by how much these landslides were actually physically connected to the river channel. And the results from those analyses were 13% were connected by count, 42% of the area was considered connected, and 37% of the landslides by volume were considered connected to the river channel. We also looked at the failure depths. And so this little plot here, this graph or table rather, when it says average failure depth, that would be the average failure depth of a single landslide surface. So when considering all of the landslides, the maximum average failure depth was 10.6 meters. The mean, or the average of all those averages, was 1.6 meters deep. And then the maximum average failure depth in Greywacke was 3.82. So I had mentioned that most of this catchment area is Greywacke, but there were some landslides that were in some tertiary sandstones and mudstones as well. So we made the distinction between those. And we also looked at the landslide source areas. So for all of the kind of the sub-catchments, I hadn't mentioned the Charwell before, but this was another kind of headwater tributary, but it didn't contribute as much landsliding area as the others. But we looked at the full catchment as well as those different tributary catchments, sub-catchments. and looked at the landslide area, and then the aerial density or the percentage of landsliding within each of those catchments and subcatchments. And this is quite an important one to note on this aerial density, because one of the things that West and others identified for the Wenchuan earthquake was that in catchments that had as low as 0.3% of landsliding area, they detected this beryllium dilution on the same or similar timescale as to what we were looking at. So we've got an area that has much higher aerial density of landsliding than some of the catchments affected by the Wenchuan earthquake, but we are not seeing that beryllium dilution on a similar time frame. And so just showing the beryllium 10 graphs again, given all of these values and given these results, we still had some questions that we needed to ask and needed to answer. So the next thing we did was we determined the theoretical amount of beryllium 10 that each of those landslides should have had in them. And we followed some equations that have been established by West and others to basically determine the theoretical amount of beryllium 10 in each of those landslides. And the important thing to note here is that compared to the Hurunui River, which is this represented by this red line over here, that kind of represents that long-term non-earthquake affected beryllium concentration signal for the region. The Conway landslides all fell below this value. And so theoretically, there should be a low enough beryllium concentration in those landslides that they should dilute or should have diluted the sediments in the river channel. So when we were still a little bit stumped, we went back to the field, probably the best place to be to try and answer questions when you're a geomorphologist. And we looked at those landslides and we looked at the potential for storage of material, because we were thinking maybe this material got flushed out of the river system already, but probably unlikely. So let's go and look at these landslides. So we considered the various degrees of connectivity. And there are landslides like this, a debris fan, that's a shallow landslide, but it's very well connected. So you can see the river right here and the landslide material coming right down to it. But there are also debris fans that were quite high up on the hill slope and not connected to the river channel. We had really big, deep-seated landslides that were deposited onto river terraces. So even though they connected with the gravel bed, they weren't actually connected to the flowing water. So at that time, not connected. And then hopefully you can see this one all right. This was one of the big landslides that created a landslide dam in the catchment. And so it's a fully connected big failure and that blocked the channel and created a lake, but has since been breached. And so that sediment is directly in the river. But we were also thinking about where this sediment could be stored. So the sediment could be stored within the lake, but potentially not a very long-lived lake. That sediment could be stored in deposits such as the landslide dam deposit, which is extremely highly cemented. Trying to figure out how tough that deposit is not too difficult when you touch it or bash it with a hammer. It doesn't want to really move at all. It's very well cemented with the very fine material. The sediment could be stored in the terraces. So in the Conway, there was about 4 meters of aggradation for about half a kilometer to a kilometer downstream of that dam. And then there's also potential for that sediment to be stored in the braid plain itself. So we've got this very wide braid plain, and the river can move back and forth across this braid plain and deposit sediment across the whole thing, but not always be in contact with all of that sediment. So there's lots of potential for this sediment to be stored within the catchment. And so kind of from this analysis and from the beryllium 10 signals and the unchanging beryllium 10 signals, we kind of had some conclusions, one of which was that connectivity does not necessarily imply mobility. So even though we had some connectivity values that were on par with other landslide inventories from other big earthquakes, you know, we don't necessarily think that that sediment has been mobilized yet, even though it could be in the channel, it might not be. It also, our results kind of challenge some assumptions of the fluvial response timescales to these sorts of events. And so again, you know, we were kind of expecting to see a relatively immediate response of this river to the earthquake, but using this method, we did not see that response. But ultimately, I think what this will contribute is the beginning of a new data set, which hopefully can be built upon. We are aware of some people working out of the University of Washington who also have some cosmogenic samples for the region, as well as some cosmogenic samples for some of the other rivers affected by the Kaikōura earthquake. And so it would be really interesting to see how this particular river is similar or different to the other rivers that were affected by the earthquake, and see how kind of the landslide distribution and the failure depths and all those different variables across the region might influence the fluvial response. And so with that, I'm just going to say thank you. I think that it's worth showing off my beautiful clean quartz again, because it was tough to get. And also wanted to say thanks again to Kevin, David, Toshi, Tim, Katie, Sasha, Claire, Andy Howell, a bunch of the UC post-grad students who helped me with field work, and Clare Wilkinson over at ANSTO as well for all of their help. So thank you very much.
Thank you, Claire. That was absolutely, I've seen a few of your talks, but nothing solely dedicated to cosmogenics like that. So I've learned a heap. So thanks.
Oh, good.
Has anyone got any questions out there?
I'm happy to go back to any slides if anyone wants to call me out on anything or share any ideas.
Do you have any LiDAR data sets that you could compare your beryllium to see if there's any?
I could not hear you very well, Dina. Sorry.
Can you hear me a bit better?
Yes.
Did you have any LiDAR data sets that you could look at?
I have LiDAR data sets?
Yeah, to see if there you could find in the differencing if there's an actual pulse going down on the Conway.
If there are what? Sorry, you're a bit breaking up.
If you had any LiDAR data sets, and you could look at the differencing in the LiDAR to see if there is any pulse that was coming downstream the Conway, like the dam, like the Conway Dam, like that moving downstream.
Okay, yeah, so I've had a look at some of the LiDAR. I don't have access to all of the LiDAR, but we did do some surveys, some structure from motion surveys for another part of my research, kind of in that rangefront area, to see if we could detect a pulse of sediment coming out of the landslide dam. And other than that, as I said, half kilometer to a kilometer or so of aggradation that we saw while we were out, you know, on foot in the field. We haven't seen, you know, with regards to the surveys we have done on the time frame that we did them, we didn't see any of that aggradation coming out of the rangefront at that stage. So did the best we could with structure from motion, but yeah. I know that you guys will have some exciting LiDAR in the future.
It's really Thanks.
No worries.
Everyone wants to know how far the cobble traces went.
Kevin wants to know how far the cobbles went.
Cobble
Is that-
tracer.
Yeah. So for everyone else, I should say one of the other things I did for my research was I traced some cobbles in that rangefront reach. And I surveyed them every 2 months for about a year to kind of get a coarse grain bed load perspective of that sediment mobility as well. And the farthest one that I was able to detect within that year traveled almost 2 kilometers. The individual cobble that I was tracing. There were some that I lost, so they could have gone a little bit farther, or they could have been buried. I don't know.
Sasha, I've got a question for you, for Claire, even though I was supervising part of the thesis. Can you hear me, everybody?
Yes.
Yep. Are there any plans to, given that there is distinct connected and disconnected deposits that point to the landslide areas, are there any plans to go back to those that are fully disconnected compared to those that are fully connected, i.e. not look into the fluvial system, but look into the sedimentary static system, and take a few surface samples from those that are fully disconnected, like high in the elevations on the terraces, and those that are completely connected, those that you can see that go into the fluvial channel, not to the braided streams. And we're looking for a factor of 2 or 3 in beryllium 10 per gram, if you want to compare it to the Hurunui. So any plans to continue independently of this PhD over the next 1 or 2 years to resample those sections and even to go back to the same sites that you did every 6 months and wait for the system to be flushed? And if we don't find it in 1 or 2 years.
That's a great suggestion, yeah. And we do have some samples. I picked some more samples up maybe a month or so ago. The Canterbury region had quite a lot of rain at the end of May, beginning of June. And so I picked up some samples mid-June from those same sample sites. We also collected a sample from the landslide dam. And Tim, I think, would like to get those processed. I think that will be, he was saying maybe we can get an honors student on board to get those next round of samples underway. But I think that's a great idea to sample kind of the different types of landslides and, get a picture of how the beryllium signal might differ in all those different types of landslides and see what sort of beryllium signal they're contributing to the river system.
Well, one thing interesting that Claire didn't point out, which we haven't kind of like delved into, was that we've done dozens and dozens of greywacke erratics and bedrocks. And this is the first time in our experience through initial chemistry with Claire at ANSTO and then final chemistry with Kevin and others at UV, was that these fluvial sedimentary greywacke deposits were a real shit fight to clean in comparison to taking 0.5 kilogram of greywacke and getting 30-50 grams of pure quartz out with a bit of repetitive chemistry. But Claire had a real battle of looking at 1.5 kilogram, 1 kilogram of initial material, and it just kept on dissolving and dissolving, which is a little bit of a surprise why these sedimentary deposits, obviously young, a lot of other crap in it, are basically fragmented representations of the bedrock. They're young. They're not all materials. Therefore, you don't have the resilient incalcitrant minerals remaining. These are just taking a bedrock, crushing it, throwing it into the river, shaking it up again with a few rainfalls and flush them down the river and pick them up later on. And they were impossible to clean. So that would be worthwhile a discussion in itself, actually. I think one of the key things that Kevin, and then later on, one of my PhD students called Patrick Adams, looking at bedrock in the Misery, is that we're now heading to do this phosphoric in the Greywacke sieved fraction in the less than 200 microns, not in the greater than 200 microns.
Yeah.
And we're also hitting it with pure sodium hydroxide. And that seems to be more successful in getting to cleaner quartz with not killing all the material than we would have normally got with 3 or 4 cycles of hot phosphoric acid. Anyway, just want to point that out.
Yeah, on that, sorry, I just wanted to say that your quartz is beautiful.
It took me a long time to get there.
Yeah. Did you end up treating the 2 fractions differently?
Slightly differently. Slightly
Yeah.
differently. So the larger fraction, the 250 to 500 microns, we did those here at the University of Canterbury. And the finer fractions I processed up in Kevin's lab. So we did have a few variations in the methods, and the biggest one being that Kevin has discovered the wonders of using oxalic acid and water baths or water leaching and things like that, which we didn't do on the larger samples. So it's part of the UC lab methods. So there were slight variations, but we managed to get some results from both of them.
Sorry, you used oxalic acid on the rock?
On the sands.
Oh, okay.
Yeah.
Cool.
Am I saying that right, Kevin? We did,
We used oxalic for columns.
Yeah.
Oh, okay, right, yeah.
Yeah. Okay.
Yeah, but that still doesn't answer the question, why did Claire walk into, really, it was a huge battle. And in comparison to our regular Greywacke, it was like night and day. And I don't understand it at the moment.
Anecdotally, David, like this, we've seen it everywhere. Every time we go to a moraine or we take bedrock, it's a piece of cake. We can go to the Kaikōura ranges, carve a bit of bedrock out of the mountain, and it separates beautifully, no trouble. You take that exact same rock and you put it in a river for 1 year and you can't do anything with it.
Yeah. And
I don't understand it. And I don't know that anybody really does at the moment.
Well, it doesn't work for granitic deposits or granitic rocks, for example. Anyway, the idea is that Patrick Adams is coming through with working with Krista in our lab is to try and see whether the sodium hydroxide addition is getting better preservation of the quartz grains. The smaller the grain fraction, you seem to wash it away when you rinse, but somehow the sodium hydroxide conch is solving that. We haven't yet gotten to exact repetition, but we're working on it.
We're happy to sort of do the legwork of some experimental work on that here if you want. Maybe we can team up and see if we can figure out what's going on.
Yeah, it'd be good for the future because a lot of even depth profiles in sedimentary deposits, it's all Greywacke. And even if you want to do moraine profiles in the sediment, like what Andy Hines done, that would be really nice in the New Zealand context. Thanks a lot.
And Claire wants to let you know that her yields are even worse.
Oh no.
Oh no.
Oh no. I'm sorry.
Oh wow, you've got a hard road to follow then.
Yeah.
Well, hold on. If that's the case, are you going, Kevin, to the smaller fractions, or you sticking to 250 plus? Kev?
Says less than.
Yeah, so you're also going to the smaller fraction, correct?
Correct.
Okay.
Yes, David's use of the word shit fight was definitely true. Has anyone else got any questions for Claire? Well then, thank you, Claire. That was really, really nice to hear that. And it makes me want to volunteer for field work, seeing all your photos as well.
I'll remember that.
yeah. Nice days only.
Right.
Okay. So guys, next month we did have a very illustrious talker, but he's pulled out due to various things, like his sample's been stuck somewhere in lockdown in New South Wales. So if anybody else would like to talk for the August slot, please.
I was actually able to get a hold of somebody to do talk for us. So John O'Griffin will be presenting on his work. He is actually, I think, from what I understand, it'll probably be a dry run of his PhD defense. So he's just about to finish up. He was supposed to be our September speaker, but that kind of interfered with his PhD defense. So that got moved forward a little bit. So it was a nice way to fit him in. So yeah.
Is that a warning that we have to be really gentle or really cruel?
I think it's a warning to be gentle, as always. Constructive criticism is the best kind of criticism. Don't be a jackass. You know, those things.
Are you accusing me of being a jackass now?
I didn't say you were a jackass. I just said don't be like.
I'm going to hop in very quickly and just remind everybody about the AMS 15 deadline for the abstracts. I really apologize that it's short notice, but it's been forced upon us by various other factors. We really cannot extend it dramatically more than a few days or a weekend. There are other schedules ahead of us to get the program and to give all the delegates sufficient time to prepare their video talks and their posters. It's not as if you can fly to Sydney on the plane and start shuffling PowerPoint pages. And the other piece of information, which is good to this audience, I'm fighting hard to get in the next 1 or 2 days to put up onto the website a form that allows PhD students and early career researchers to request a waiver of registration, which will help. In addition, AINSI is supposed to be coming around in the next 1 or 2 days to confirm, hopefully, that they will also support their PGRA students and those that are associated to ANSTO in portal works. Doesn't mean everybody's going to get it, depends on how much money we get. But the aim is to try and support students with good abstracts and that are matching the theme of the conference. And we have to include the word diversity representation throughout the successful applicants. So now keep posted and keep on plugging the website to see any new additions. And write your abstracts. Now, don't delay. Don't leave it to the 11th hour. Just chuck them in. Okie dokie. Thanks a lot.
The other key thing from us. Am I still not getting through?
Just come a little bit closer to your microphone.
A real close up.
Did you brush your teeth today?
Yes. Can you hear me good now?
Yep.
Okay. So the other thing from the Cosmo Collective is we are still putting together a meeting for early next year. Hopefully in person. We'll see how things go. But we've got a site, the Westport UC Field Station is the current venue that we're working with, and that survived the floods, apparently, according to Sasha, and we're going to be checking out internet connectivity and everything in the next few weeks, thanks to Sasha. The only thing we've got to do now is set a date, and then we can get sessions and everything sorted out. So we sent out a few weeks ago, or maybe a month ago now, maybe more than a month ago actually, a little poll for this group to fill in about dates. They were all in early February. We actually do have a bit more freedom with dates now because the field station is available for more time than we originally thought. But we think that early February is probably going to suit people better with, with being before teaching starts. So we're going to look to finalize a date in the next few weeks, I think we can say. So if you didn't see that Google poll, we can send out another reminder and you can all have a look and just check off what dates are most suitable for you. And then we'll have another meeting separate from these monthly meetings, but a meeting where anyone who wants to be involved on the organizing of that meeting can come along.
Give me just 1 second and I can put a link to it in the chat. And you can just go do it. Hang on. It's not letting me share it. I'll make sure to send it out to everybody in just a couple of minutes.
Okay, well that's all from us, I think. Is that right, Ross? Do you have anything else to bring up? Sasha?
I'm good.
Oh, that's good. Thanks. It was a good session. Thanks, guys. We'll see you next time.
Oh, I actually just got it. Hang on.
Ah.
Sorry.
That's awesome.
So that should be the form. If you wanted to hop in there and fill it out real quick for us, that would be great.
Again, Claire.
Okay.
Thanks again, Claire. That was
All
a
right.
wonderful talk.
It was.
Oh, thanks for the opportunity. All right.
Okay. I might as well sign off then. See you guys later.
Bye. Thanks,
Bye.
everyone.
Thanks.